Hi all, my name is Mads Barnkop from Kaizer Power Electronics. This is part 4 of the AGFA ADC 5155 X-ray image scanner or digitizer. And today we're taking a look at the heart of the computerized radiography, which is of course the photomultiplier tube along with its high voltage power supply. So we're going to do a teardown of these two units, and hopefully we're going to do some reverse engineering on the photomultiplier tube, and then see if we can do some detection with some scintillation material, and maybe see if we can detect some cosmic rays with this. So let's get this taken apart. We have the high voltage power supply, and we have the photomultiplier tube itself. Now, this all connected up to the computer. So if we just bring that front up, we can see that we have 4 connectors here at the front. One is the red high voltage power supply over to the PMT itself. Then we have the first connector here, just 3 pins. That also goes over here to the PMT assembly. The next here is a 24 volt plug. As we can see, that corresponds to the front of the computer. And we have a 6-pin plug here, which is the high tension control. And then we have the 9-pin connector here, which is the serial connector or IV converter. And I'm not quite sure if this is just a TTL level signal or 3.3 volts, or if it's even just a regular serial output. But we will see once we get inside this box here. So we can just take a peek inside here and see that's connected to 4, 5, 6, 7. So that does not seem to actually be a regular serial connection that would sit on 2 and 3. So we can safely assume that this is not a RS-232 signal coming out of the PMT. Whoops, what is going on here? That actually just jumped right at me. Okay, this is not what I expected. There's not even a large PCB sitting in here. But I can disconnect the whole PMT assembly here. See, here we have a very nice PMT here, which is a photomultiplier tube. Sits on these springs in order to spare it of any mechanical stress. Possible implosion. So this is a vacuum tube. Yes, we knew that. It's tested in 1998. Let's see this serial number and tube type. S83021E and then 14 written in hand. Source CO57, so that's the test source. And the scintillator number, that could probably just be their test scintillator material. But that sure does look very nice with its own socket. Has the voltage sharing resistors mounted down here at the red ring. So let's just put that to the side again and see what's inside here. So it's not much more than a shielded metal shield enclosure. Sitting down here where the tube was, the high voltage power supply, just a single line in and then grounded to the chassis. And then we have this small board. So this chip we have here, the W23100, is a read relay chip. which has 2 relays. But other than that, it's just passives, capacitors, resistors. So we assume that is some kind of filtering or just passing the signal through here. Yeah, actually not much, so perhaps it's just triggering a output when it reaches a certain level. So it's not even sure that I'm going to reuse much of that. But we will see once we get it fired up. But boy, does this look interesting. Heim Electronics. So we have a power supply here with minus 1.5 kilovolt at 6 milliamps. But look at this. This input range, that is where this gets interesting. We have the plus 24 volts. And do we even have a ground here? High voltage just, yeah, power 0 volt. Okay, so pin 10, which is the tube black here, and also the minus for the analog input. That's ground on the black wire. Then the gray wire here sits on the plus 0 to 10 volt analog input. Then we have a bridge here, which says it's remote controlled. And we have a V monitor, 0 to 10 plus volt. So it can also give a feedback of the voltage output. Now that's a very nice little power supply here. And the small print we have here on the side consists of a AD823, which is a dual operational amplifier, and we have a AD620, which is a single operational amplifier. So this is the connection up to the high voltage control. The 24 volt DC comes in here, goes straight through to the high voltage power supply, but there's also a small DC-DC converter which supplies plus minus 15 volt DC for these 2 operational amplifiers, which connects to the high voltage control. And over here we have a 3-pin connecting up to the PMT module. And the high voltage power supply in all its glory. We have a single UC3525 controller sitting here, driving what seems to be a pair of MJE305 transistors. So we just have 2 power transistors driving a small transformer. And it have a CV multiplier going through a load resistance, and then we have a lot of capacitance coupled over the output stage in order to not pull it down too quickly. And here we have I actually thought that would be some kind of measuring resistor. Start Electronics CD85. Okay, I'm wondering what that really is. But as it is connected to the high voltage output and then loops back, which seems to be bridge over different parts here, I would assume that it is some kind of high resistance network in order to get feedback from the high voltage output. We can also see a nice detail here that is formally coded from around here and up, but not down here on this part. So it's only a coating in order to minimize corona. And you can see they really smeared on the soldering down here, and that is to avoid any kind of corona on the high voltage part, to make any pointy object as round as possible. And a small CE mark. On the back side of the connector board to the power supply, we can see that the 3-pin connector that goes to the PMT assembly, that is a plus minus 15 volt DC supply from this board to the PMT assembly. In the middle we have the 24 volt DC power supply, which just goes in here and goes directly up to the PMT or to the high voltage power supply, which then has the high voltage cable over to the PMT assembly. And over here we have the high voltage tension control, which goes through the two operational amplifiers. So I think I will bridge over the whole control here and then just use the 0 to 10 volt analog control with a potentiometer on the power supply. And I will solder in a new connector for the 24 volt DC supply so we can omit using the whole computer part. So to bridge over the whole analog control of the power supply, I just have now a 24 volt DC input, a 47K potentiometer with a 68K resistor in series with one of the legs, and at 24 volt DC that should give me 0 to 9.5 volt out on the middle pin, which has now been soldered on to pin 5 up here for the connector to the power supply. So let's just get all this put together and fire up the power supply and test it. I now have a potentiometer mounted here at the front of the power supply. I can feed it 24 volt DC in from external without using the designated connectors here, because I do not want to cut open that cable in order to just feed it in 24 volt DC. I hooked up my Elmer multimeter here because it can measure up to 1000 volt DC. So I have that connected to the output end of the BNC plug. So let's just try to ramp up the 24 volt DC here on the power supply, and we can see we're actually getting some output already. So let me just get that up. Seems to be just some kind of baseline. Oh. Okay, as I passed 20 volt DC, it made a little noise. Seemed like it was actually switching on. Okay, so here we have it. A negative 1.5 volts on the output. So let's try to turn the potentiometer. And we are already at minus 130. So let's just see if we can get up near 1000. I will have to stop before reaching 1000 because the multimeter cannot go any higher. Oops, but now there can the knob here. So I guess the high voltage adjustment potentiometer that we have down here at the power supply is adjusted way below the capability of 1.5 kilovolts, as I'm only at minus 600 right now. But that also makes sense that these PMT tubes used for image scanning are not driven that hard, so they usually use a lower voltage on the whole photon acceleration chain. So now the whole setup has been connected. We have the power supply connected with the plus minus 15 volt DC, along with the other plugs, the output signal, and the high voltage connected to the PMT assembly. So right now there is no kind of crystal or any input to it, so it's just sitting in darkness, pointing downwards into the table. And I have hooked my oscilloscope up to the 3 channels that are not ground. So I assume there's 1 common ground and 3 signals out. So let's just try to find out. Let's first turn on the power supply again, just like that. Okay, and it seems like we are picking up nothing. But that was also expected. Perhaps we can see a little bit of 50 to 100 hertz noise there. So yeah, right now, nothing. So I will try to mount a crystal on it, and we will see if we can pick up some particles going into that. I have 2 pieces of scintillation material, so I will first try out with this round one, as that has the nicest surface and would probably give off the most light compared to the relative rough surface of this square piece. Right now I have the crystal sitting underneath here, wrapped around in aluminum foil. So let's just try to turn on the power supply again. First the 24 volt DC. Get that up there, and then the negative voltage on the tube. Okay, so it has been hard to find any peaks, but I can see we have what I presume is some blue negative peaks. Yep, there we have it. So let's get to trigger on second channel instead. And move the trigger downwards. Let's see if we can find anything. We'll have to single shot our way. And there we have it. We have a detected particle. Let's try again. So the randomness of when we get to capture something tells us that this could perhaps be particles. And we also have to notice the changing height here. Let's just get some measurements here. It's actually very, see, minus 256 millivolts. So let's just try to trigger that again. Minus 184. Minus 228. Minus 176. Minus 268. Okay, so a lot of this I would contribute to the relatively low voltage that we're driving the tube at, that the light glimpse is simply not getting accelerated into a very high pulse here. But at least we can see the power supply is working. The scintillation material crystal does give out a light glimpse when it's hit by some kind of radiation, and we can actually measure the energy density. But as this is not calibrated, there is no way to tell what kind of material hit it. But if I did calibrate it with a wide variety of sources, I would actually be able to use this to identify what kind of radiation source that I was detecting. I really hope you enjoyed the teardown and reverse engineering of this high voltage power supply and the PMT assembly. And if you want to learn much more about the photomultiplier tube and how that works, I did actually reverse engineer the same assembly, just not from this ADC solo machine, but from a duo machine, which I actually think was a later version that used a newer computer and actually had a lot of the IV conversion logic sitting inside the tube assembly itself, so it would put out a much nicer signal that you could readily use in your computer while picking up data. This clearly is a raw signal that we get from this. Now the experiment is still running over here. I'm looking for peaks that goes beyond 500 millivolts, but so far it has not detected any. And as a small addition to the lab here, I have added a monitor up here which shows the live statistics for the YouTube channel, but also visitors to kaiserpowerelectronics.dk, and that is also where you can find the article on the other photomultiplier tube, reverse engineering, and also some of the theory how that actually works. So if we had some more visitors right now, we could actually see over here on the small map right now a single visitor from South Korea. And on the YouTube channel, it's at 2,215 views the last 2 days, which is super nice. Thank you guys for following. So until next time, see ya.